Today we're going to demystify the incredible technology of ultrasound. We've all seen those grainy black and white images, right? But have you ever stopped to wonder how it's even possible to create a picture of what's inside our bodies using nothing but sound? Well, let's dive in.
So yeah, that's the big question. It really does seem like magic, doesn't it? But as we're about to see, behind every single ultrasound image, there's a story that starts and ends with some seriously cool physics.
All right, to get this journey started, we first need to meet the hero of our story, the sound itself. And trust me, it's a kind of sound that's completely unlike anything you've ever heard before.
Now, you might be thinking of something like an X-ray, but this is totally different. An X-ray is a form of light. Ultrasound, on the other hand, is a physical, mechanical wave. It actually needs stuff to travel through, like water or, in our case, human tissue. It's really just like the sound of my voice, with one huge difference. Its frequency is way, way higher.
Just to put this into perspective for you, the absolute top range of human hearing is around 20 kilohertz. Medical ultrasound, it starts at 1 megahertz. That's 1 million hertz. So we are talking about a sound pitch that is at least 50 times higher than anything you could possibly hear. And it's this super high-frequency pulse of sound that we're going to send into the body.
Okay, so how on earth do you create a sound that high-pitched? It's not with some tiny little speaker, I'll tell you that. It's actually through a pretty remarkable physical phenomenon.
The real magic happens inside the ultrasound probe. You know, the part they put on your skin. It's packed with special crystals that have this amazing property called the piezoelectric effect. Basically, when you zap these crystals with electricity, they vibrate like crazy, and that's what creates our high-frequency sound pulse. But, and this is absolutely crucial, it also works in reverse.
So the ultrasound probe, or transducer, is doing two jobs at once. First, it acts like a tiny, powerful speaker, sending that sound pulse out. And then, instantly, it switches roles and becomes a super sensitive microphone, just sitting there, listening for any faint echoes that bounce back.
All right, our little sound pulse has been created, and now it's launched on its big journey into the body. But, you know, this path is not exactly a straight shot. It's a journey filled with challenges and, as you'll see, some really important trade-offs.
And this right here is probably the fundamental challenge in all of ultrasound. If you use a really high-frequency pulse, you get a beautiful, crystal-clear, high-resolution image. The problem is that energy gets used up really fast, so you can't see very deep. On the flip side, a lower frequency pulse can travel much, much deeper into the body, but the picture it creates is going to be a lot less detailed. So the sonographer has to pick the right tool for the job.
Now, as this pulse is zipping through the body, its speed changes depending on what it's traveling through. I mean, look at the huge difference in speed between soft tissue and bone. To make things manageable, the ultrasound machine does something really clever. It just assumes one constant average speed for everything, 1,540 meters per second. It's a brilliant little shortcut that's accurate enough to build a clear picture almost all the time.
And just like a runner in a marathon, our little sound pulse starts to get tired. It loses energy the deeper and deeper it goes. There's a technical name for this. It's called attenuation. Basically, some of its energy gets absorbed, some of it scatters, and this is why it's so hard to get a good look at things that are really deep inside the body.
Okay, here we are. This is the climax of our story. We've sent a pulse out. We know it gets weaker as it goes, but how does any of that create an image? Well, the secret is the echo. It's all about what causes it.
So I need you to remember this term, acoustic impedance. The easiest way to think about it is like a unique sound personality for each type of tissue. Your liver, your kidney, your muscle, your fat, they all have their own acoustic impedance. And here's the key. An echo is only created when our sound pulse crosses a boundary from one impedance to another.
So, let's see how this actually plays out. Imagine our sound pulse is traveling along and it hits the boundary between two similar soft tissues, say, between the liver and the kidney. As you can see, the difference in their sound personality, their impedance, is really small.
Because that difference is so small, it creates a very, very weak little echo. Most of the sound just keeps on plowing ahead, deeper into the body. The machine hears that faint echo come back and says, okay, that's a shade of gray.
But what happens when the pulse hits something totally different, like the boundary between some soft tissue and a solid piece of bone? Well, now, the jump in impedance is absolutely massive. The same thing happens, by the way, at the boundary between tissue and air. The difference is huge. This huge difference creates an incredibly powerful, strong echo. Almost all of the sound's energy just bounces right back to the probe. The machine sees this powerful return signal and paints a bright white pixel on the screen. This is why bone and things like gallstones show up as white. And, aha, this is the exact reason we need that cold gel. It gets rid of the tiny layer of air between the probe and your skin, which would otherwise reflect all the sound before it ever got a chance to go inside.
Okay, so at this point, the transducer is being bombarded with thousands of these returning echoes. Some are strong, some are weak, they're all coming back at different times. How does the machine turn this absolute symphony of chaos into a picture that makes sense?
Well, it does it with what is essentially a super fast, super precise stopwatch. The machine knows the exact moment it sent the pulse out. It then just times how long it takes for each echo to come back. If an echo comes back really fast, it must have bounced off of something shallow. If an echo takes a little longer, well, it must have come from something deeper. It really is that simple. The machine does this thousands and thousands of times every second, sending out pulses in slightly different directions. It maps two things for every single echo it gets back: its strength, which tells it how bright to make the pixel, and its return time, which tells it where to put that pixel on the screen. And just like that, it paints a picture, line by line, completely with sound.
This quote right here just sums it all up perfectly. That image you see on the screen, it's not just a picture. It's a direct visualization of the physical properties of your tissue. It's a map of acoustic impedance, built from nothing more than the timing and the strength of returning echoes.
So, the next time you see an ultrasound, I hope you remember the incredible journey that tiny sound pulse took. It's just an amazing testament to how we can use the basic laws of physics to see inside ourselves. And it really makes you wonder, doesn't it? If every single one of these echoes tells a story about the structure it just touched, what else could we learn if we just listened a little bit closer?